to another concept problem session. Today will be problems. Okay, so before I get carried away with that, let's talk about um, you subscribing to this channel. If you subscribe this channel actually gets more visibility, and if you hit a like button, something like that, it gives a good feedback to me and feel like it made an impact to you. Anyway, so if you have a question, you can just leave comment and I'll do my best to reply to that. So we're building on what we did in last session. So we talked about in the last session we talked about thinking about dynamics, which is F equals to either dp dt, mass fixed, then it becomes mass times acceleration. But today we're going to just have that. This will be in the future. Okay, so examples, I'm going to do 2 standard examples. And we're going to build up more examples later, but I just want to get your feet wet. So number one is a so-called inclined plane. So only one object is moving. So this will be only one object moving problem, okay? But there's in here angles, etc. It's a problem about how to think about angles and directions, okay? And it's a laboratory, it's a test whether you can, in a simple setting, can deal with vectors. Okay, that's second example we're going to look at. And just to draw this, it's going to be like either it's going to be a plane like this, maybe a wedge, and this is fixed, and there is a block of mass m that's going to either slide up or slide down. That's going to happen to this block. All right. So that's called inclined problem. And second problem is, I hope I can get time to do it. It's a potentially two objects moving. And one example is, here's a table. This is fixed. And it's got a smooth surface. It's a smooth surface. So it has a smooth surface. And on that, you place one box or a book. And on top of that, you place another book. And either you put a force on that or put a force on that. So let's see if I put a force on that. And the question is, so this surface of contact, and there's another surface of contact. So these are given as maybe mu s and mu k as coefficient of static and kinetic frictions. And for this surface, say mu s prime, mu k prime, and we'll say these guys are less than that. Mu s prime less than mu s, okay? And this force, I keep increasing in time. So it will be like, if I take this force and say this is mass m1, this m2, and with time I keep increasing, and there comes a time t1 when it slides on this, so this whole thing start to move. It start to move at t1, but I keep raising the force, and there comes a time t2. So while this is sliding, that thing also start to slide. So this is m2 start to slide, on m1, and at this instant m1 it starts to slide. So we have to figure out what is this f1, f2 values are. What are these values that will happen given those things? Okay. All right, so this is two things potentially moving. So we'll see. Let's do the inclined plane first. All right. So inclined plane. Let's look at that. Rewrite that. So you can have inclined plane like so, or you can have inclined plane like so. It's the same situation. You put a box here, and you put a box here. So if you look at this is the surface of contact, and in that surface of contact there will be contact force. We don't know which way the force is pointed, so in the surface of contact you can have a force along it, or you can break it up in two different forces. So either this way or this way. Okay, so one way to do is these two forces, surface of contact, we will say it's going to be static friction or kinetic friction. So these forces, one of these will be the case, but it will be either static friction or kinetic friction. So these are like a friction, and this will be a normal force. And then of course you're going to have really vertical, straight down, parallel to the vertical axis. At the center of mass is going to be gravity, Fg, and the gravity is value is, if this is mass m, so we're going to always use mg, and we're going to stay symbolic. I don't want to go into the, if the numbers are given, you work it out symbolically and then put the numbers in. If you're not comfortable with just symbols, you're going to be trolled. You're going to make a lot of mistakes early on. So it's best to get used to the symbols. Okay. So this is theta. Sometimes you're going to get theta 30 degrees. So just to not scare people. The numerical values are given not to scare people, but if you're so easily scared, you are not going to be able to solve problems in the test situation. Okay, so best is to do the problem in a symbolic way. Just do it many times. A month or two will pass, and then you will become, by then your brain will adjust that. You'll force your brain to adjust thinking symbolically, and then numerical thing will just be not that difficult. Okay, all right, so let's I'm going to define the problem that I put on it and it's not sliding. So this case 1, I place the box but not sliding. Place the box but it's not going anywhere. Okay, so clearly something is holding it. So you have this force, and this force is going to be there because you are pressing on the surface. So this wedge is applying a normal force on the block. Okay, so the forces, if you look at the force situation, two forces you already know. You have Fg and you have Fn, and they're pointing in different direction. So if these were the only forces, then their sum will be pointed in. So if you add these forces, so the way you add vectors, if you have vector A and vector B, so these are two vectors because they have a direction. One way to add it is just complete this rectangle. So this will be their sum from, if you draw from the same point. So that's where the free body diagram is done. So everything draws from the same point. So there will be there has to be a third force. There will be non-zero force. Suppose I draw it very poorly, and I drew it like this, Fg, but I kept this guy. Maybe I made it really big. Then it will say that there's a force. Net force will be in that direction. But since I don't know which way it will be, this is correct, that's correct. We don't know that. So there will be a leftover force. Basically, this is, if I have, this is force Fn. If this is only two forces, then this is leftover. Okay, so this is leftover. So it's saying it's not going anywhere. That just means acceleration is zero. If acceleration is zero, velocity is also zero. But when we apply F equals ma, so if I do F equals ma, when I apply that, what information can this give us in this situation? Well, that's what we're trying to find out. What can we get from this equation? But maybe many questions can be asked about this kind of problem. I'm just trying to give you what is possible when trying to solve this kind of problem. So there will be some left over. Then we say, okay, the only thing will be along this contact surface. There is no other force. Maybe suppose this problem had a force, somebody was pushing this force F0, somebody is pushing, then oh yeah, there is a force like that. Oh, okay, there's a force like that. But it's still, these three may not add up to zero. They have to add up to zero. You know, if I have this situation, then of course it's not going to add. Then this going to be, the net will be this plus that, and so net will be that. It's not going to add up zero. So I have to be knowledgeable enough to say, hey, in this situation, most likely the force is to the right, and let's say I don't have this for simplicity. Okay, just these two. Force have to be force of these guys and these guys have to be right. So there has to be a static friction, a friction. So we have pointed up. Now static friction can point down sometimes depending on the situation. So, but here a static friction has to be pointed up. So now that's the hard part, figuring out. So this is Fg, this is Fn, 90 degrees, and we have a static friction. For somehow all of this is balanced. Okay, this is balanced, so it's not going anywhere. Then it would mean that this adding these three forces will go to 0. So mistake number one, what is mistake? Just say Fn plus Fs plus Fg equal to 0. Mistake number one. Mistake number two, Fn equals Mg. So these are both mistakes. Okay, you can't write this thing in this constitution. You don't know Fn and you don't know Fs. That's the two things you don't know. And you can figure both of them out in this problem, okay? So this is the theta. Theta is known. Theta known. M known. So in this kind of situation, question that will be asked by placing the box like that is, what is Fn, what is Fs? Okay, so what is Fn, what is Fs? These two only questions can be answered. Okay, so let's see how we're gonna answer those questions. If this is theta, then if you draw this line and hit it here, this kind of 90 degrees, this is 90 degrees, so this will be 90 minus theta. The dot is 90 minus theta. So if I extend this backward, this will be, this is 90 minus theta, so this has to be theta. So theta migrates over there. It's very important skill to migrate theta properly. Okay, next thing we do is think of F equals ma as fx. So this is the net. We think of this net equals ma. So what fx net will be if I have three forces here. So fx net and fy net, ax, ay. So think as components. So what is f? Let's look at just fx net. Okay, what is fx net will be on the left side? The left part will be equal to fx of this gravity plus fx of the normal plus fx of the static friction. And fy net will be fy of gravity plus fy normal plus fy static. So this guy will be like that. So these two equations actually are basically what is saying that if I took fx gravity plus fx the normal plus fx of, if I add them up, it will be mass times ax, fy gravity plus fy normal plus fy static friction. So that's all that equation says. This equation says this, but it doesn't tell you what x and y axis will be. It doesn't tell you what x and y axis will be. So I am free to choose orientation of my x and y axis to simplify it, the calculation. Completely free to choose. So, and also free to choose origin, okay? But this only direction matters. So if you look at here, if I okay, let's see a wrong choice. let's make a stupid choice and then make a good choice. Okay, here is a stupid choice. A lot of people make this choice. Fs, Fn, and they will say, hey, this is going to be my x, because that's the way I always know x goes, and this is going to be my y, and so this is a so-called, I call it a stupid choice. Can you tell why it's stupid choice? Well, look at this. Only this guy is along the axis. If there was acceleration, if this was not, say if this was not going anywhere and there was acceleration, suppose if accelerating down, accelerating will be that way. If there was acceleration, okay, if it pointed down or pointed up, it will be along the incline. So in this stupid choice, I have 1 vector, 2 vector, 3 vector, 4 vector to deal with, and only this guy is along the axis. Everybody is off axis, so I need to figure out these angles, these angles, these angles, these angles, break the. So each one of them is going to lead to trouble. So find to minimize the work. So what if we said, okay, this is going this will be my x-axis. This is very, very bad drawing. Okay, maybe I'll even do down. Going down is going to be my x-axis, and it will be fy axis. All they have to be is 90 degrees. So fg, this is the only one not in the axis. If this is theta, we already worked out this angle is theta. So we already know with respect to this, we don't know if there's x-axis, but there's the y-axis. So everything is pretty clear here. So if we do this, then fsx equals to minus fs. Is the whole force is there. This is the magnitude of the force. X pointed down, and this guy is in the opposite direction. Fn, but fsy is 0. Fnx is 0. This guy is all along the y-axis and has a positive value along the Fn. Fny is entire Fn. This guy, I have to be careful. So if I do on the x-axis, this projection is going to be positive. That much will be fgx. And that is going to be on projecting the y-axis is the same as that. And in this triangle, this is the opposite of that angle. So it's going to be sine. This thing is the whole thing. This is fg whole thing. Mg value. This is mg. So it's going to be mg sine theta, and it's going to be plus because the projection is plus. When I project on the y-axis, that's the y part. So this is going to be negative, and it's adjacent to this angle. So fgy will be minus mg cosine theta. Of course, ax is 0 and ay is 0 here. But if that was the case, we would have worked out acceleration also. So from this is trivial to this plus this plus this equals 0. So minus fs plus 0 plus mg sine theta equals 0. 0 plus fn minus mg cosine theta equals 0. And this tells you fs equals to mg sine theta and fn equals to mg cosine theta. And you can, sometimes people ask for what's the ratio of this fs over fn equals to tangent theta. Okay. A very famous problem on this is, so it doesn't tell you coefficient, doesn't tell you mu s. Why? Well, we don't know if this was the largest amount of static friction that was possible. That's why. Okay, that's because we don't know if this fs value is the largest. Fs can be between the two, between the wedge surface and the box. Right? That's why we don't know. So often problems are designed to actually get this. So what you say is, okay, I have this surface and the incline is very low incline. I put the box, doesn't slide. Okay, then I move the incline more. Okay, no slide. But then over here I reach, it starts to slide. So the box is like that. So this is the angle, this is theta max. Of course, this will correspond to, if you look at now fs here, just before theta max, almost maybe theta max minus epsilon, very tiny amount, of small angle. Okay, it's still not sliding. So if angle like that will be like this angle, so that's the theta max minus epsilon. So let's call this theta max, which actually is already sliding, but this one doesn't slide. This immediately before that, this angle theta max, when we have theta max, fs is going to be mg sine theta max minus epsilon, and fn will be mg cosine theta max minus epsilon. So you can see that this would be at epsilon, when we say limit epsilon goes to 0, this will go away, and this value we'll call it max. All right, we don't call this min, but this is the max. So now fs max over fn, that will be static friction, and that's going to be sine theta max. All right, so that's the way static coefficient friction is coming from a limiting process. All right, when it starts to slide, if theta is anything more than, if theta greater than theta max, slides means you don't have still friction, but you now have kinetic friction, and you'll have a Fk, which usually written as mu k Fn. You can just leave it Fk, or you can replace with mu k Fn, and mu k will be, mu k is not mu s. Usually mu k is smaller than mu s. Okay. All right, so that's a very classic problem, and what we can gain from it. I think I won't have time to do this one, but let me just make this case one a little bit more complete. So let's see example 2 along the same thing. So now the work will be very small. Suppose I put a box, I put a force F0, and it's sliding upward, okay, and mass is m. So find acceleration in here, and find everything else you can find. All right. Okay, so again, we just first look at the forces that's there, the normal forces, and this is horizontal. Okay, so it's in the same direction as that. These are parallel. And because it's sliding up, the velocity is that direction, the kinetic friction will be pointing the opposite to the direction it is moving. Fk opposite to V, not to A necessarily. It may have been slowing down, who knows, it's going up. Okay, maybe acceleration, maybe going up but slowing down, then the acceleration pointed down. So maybe, so if going up incline but slowing down, if that's the case, then acceleration is pointed down. If speeding up, then acceleration will be pointed up, and these will show up in the, when we set the problem in components, will be either positive or negative. So let's see, just like last time, we have Fg, this angle theta, we have Fn. Now this time I have Fk, and see this is coming in, but I write is starting from here. Just displace this so that I can write with the beginning here, F0. So if this is theta, then that's theta, and we already worked out that this angle will be theta. Again, we just and we'll just say we don't know acceleration. Acceleration as component is going to be if this is this is the x-axis and this is the y-axis. If that's my direction, acceleration some value a, and there will be no zero. F0, Fg, the Fk will be, this vector will be some minus Fk, no y, and this will be Fn 0, sorry, the y-axis, Fn vector will be 0 Fn, those are components, and this we already worked it out. This is mg sine theta minus mg cosine theta, and ignore z, okay? There's no z here. Z is perpendicular to that and nothing is happening there. And this will have a negative x and a negative y, and a y will be sine and x will be cosine. So this will be minus f0 cosine theta minus f0 sine theta. Now all the axes added up. Let's all the add axes. So start from here. So mg sine theta, then go with that guy minus fk plus 0 minus f0 cosine theta. So this is the fx net, and this must equal to mass times the x part of acceleration a. We just leave it ax. So we know we're really finding out ax. So this is one equation we can get. And for fy net, I do the same thing. Start from minus mg cosine theta. Fk gives me 0. This one gives me plus fn. And this can f minus f0 sine theta equal to 0. So what kind of things you can be asked to do, okay? And what can you be given? Suppose you're given f0 is given how much force you're applying. You're also given m, and you're also given the angle, okay? And you're also given mu k. So these are given. To find Fn and A. So these things you have to find. Now it's a matter of algebra. So this one, just replace this mu k Fn. So that's given. So from the second, I can find out Fn. F equals mg cosine theta plus f0 sine theta. Everything is given. Now, I was telling you earlier that some people just, when you look at the Fn, their gut reaction is mistakes like this, okay? Say Fn equals to mg. Fn equals to mg cosine theta. These are mondo mistake, big mistakes. See, Fn is, this is definitely not mg cosine theta. And this is why I picked up this example, because illustrating that these kind of mistakes very common. People just memorize this formula because they solve some problem, and bingo, they got caught in a physics professor's net, you know. So that's not. So we got the Fn by doing this, and now if I put Fn in here, I will have Ax. So from there, ax will be 1 over m mg sine theta minus mu k, this whole damn thing here, minus f0 cosine theta. So that these are the answers you're going to get right away. And ax will be if this is say this is positive, then is pointed down because my x-axis is pointed down. X-axis pointed down is towards the positive x-axis. If this turns out to be negative, then it's going to be pointed up because the x-axis is pointed down, but the a is pointed up. So a is pointed in that same direction. So depending on the numerical values, you might get a positive or negative, so I don't want to really prejudge it. Okay, so that's it. I think I'm going to do the other problem more carefully. It's not necessary to rush it. This kind of things very takes time to appreciate, and I'm glad we took time to go over detail of this. I hope some of these become clear to you, and I hope you learn about some of the traps when you're trying to solve F equals ma problem on a box and an incline. Okay, there are many problems in any textbook. You can go and try to practice. So I'm going to stop here and see you in the next video. Definitely don't forget to either subscribe to this channel or click the like button. Very few people who come to this channel actually do that, but it actually helps out a lot. Take care. Bye.